All right. All right, thanks for coming back, everyone. Just a reminder, so we have our first problem session tomorrow at the same time, led by Chris Sloan. So I hope you've had a chance to work on some of the problems that are on the website. I'll post the second problem set soon, and there'll be a problem session for that next week. All right, so first, just a reminder of what we did in the second talk last Thursday. We talked about Berdan homology, and we did a few examples, including the sigma suspension for C2 of Hz, and for C4, we did the lambda suspension of Hz, and a couple of other examples. And then we talked about the slice filtration for a general group G. And I had hoped to get some examples of some suspensions, some representation suspensions of Eilenberg-MacLane spectra. We didn't quite get to that last time, and so that's where we'll start today. Okay, so again, that's the plan for today. And then the other main topic for today is going to be a discussion of ROG grading, so grading over not just integers, but representations or virtual representations. And again, I was originally hoping to do some discussion of duality. You can probably hear that beautiful noise outside. Some discussion of Anderson duality and so on, but it looks like that'll probably wait till next time. All right, so let's get started. And so on the problem set, one of the problems asked you to think about some of the suspensions of Hz for the group C2. And in particular, I asked you to show or think about why this is an n slice, at least for n in the range between 0 and 6. And it turns out that is exactly the range in which it is an n slice, and for other suspensions, it's not. So again, in this range, the slice and Postkov filtration coincide, but outside this range, they don't. And so let's just consider the first example that's outside this range, and that would be the 7 suspension of Hz for the group C2. And so we might wonder, well, is this a 7 slice? Now for the group C2, we know that always suspending by a regular representation just shifts your suspension by the order of the group, right? So for C2, suspending by rho just shifts things by 2. In particular, if we're wondering if something is a 7 slice, that's equivalent to wondering whether it's the 3-row suspension of a 1 slice, okay? And the good thing about that is we have some understanding, an explicit understanding of what 1 slices look like. They're all 1-fold suspensions of Eilenberg-MacLane spectra, with the condition that the restriction maps in our Mackey functor, are injective, okay? So if we're asking if this is a 7 slice, we're really asking, is this C2 spectrum of this form where M has an injective restriction? Okay. Great, so if we're trying to understand this more concrete question, let's just desuspend both sides by 3-row, okay? And so now we're asking, okay, is this equivariant spectrum, is that a once suspended Eilenberg-MacLane spectrum, again, where a Mackey functor has an injective restriction, okay? And now this is exactly one of these examples of things that you were asked to think about. This is part of these Berdan homology calculations that we did some of together. And on the problem set, I asked you to think about more and to really complete that story for the various suspensions of Hz. And so particularly, if you did that exercise, you may have computed that this one gives you the one suspension of, so this is the Mackey functor Q Z sigma. I'll remind you what this looks like. So Q Z sigma, at the bottom, this was the sine module, and at the top, it was a Z mod 2. And we had a surjective transfer map from the sine module to the fixed points, which are a Z mod 2. Okay, so that's that Mackey functor. And so it turns out that that's what you get when you compute this, okay? Has only that single non-trivial Mackey functor. So again, we're asking, is this a 1 slice? And well, as we know, that's equivalent to asking, is the restriction map injective? Okay, but it's not. The restriction map here is 0. It's not injective, so this is not a 1 slice, okay? So let's decompose. And so, well, we know what the 1 slice is. What we're supposed to do is take pi1, And so that pi1 Mackey functor is this Mackey functor we're talking about. And we're supposed to mod out by the kernel of the restriction, okay? And so here, if we look at this Mackey functor, the kernel of the restriction, well, is all the fixed points, right? Everything on top is sent to 0 in the restriction. So when we mod out by that, we're just gonna wipe that out, okay? And that's gonna give us the one slice. So if we do that, so if we mod out by the top, we get this Mackey functor, which is just that sine module Mackey functor, which vanishes at the top. And then we have a quotient map, and the kernel, everything that we wiped out is just that z mod 2 at the top, which again is this Mackey functor that I call G. It's this geometric Mackey functor, which vanishes at the underlying level. And now this short exact sequence of Mackey functors gives us a fiber or cofiber sequence in the world of equivariant spectra if we turn them into Eilenberg-MacLane spectra and shift them up by 1. Okay, so we have this cofiber sequence of C2 equivariant spectra. And so again, the whole point was that when we do this, the one on the right is a one slice because now it has an injective restriction. So we have this thing we're trying to understand. We've mapped it onto something which is a one slice. And then the fiber is this spectrum. But now this is an example of something that we looked at before, and we know this is a two slice. Okay, so one way to see that is that this is one of these geometric inflations. And remember, because of the order group, that doubles the slice dimension. So at the fixed point level, this one is the one-fold suspension of H z mod 2, that ordinary spectrum, which is concentrated in degree 1. And when we inflate it, then we get this thing, and that doubles the slice dimension. So that's a two slice. So now this cofiber sequence, again, as we said in the first talk, if you have something that looks like a slice filtration sequence or slice fibration, then it is one. And so this is the slice tower for this middle C2 spectrum. And then we can resuspend, undo this desuspending we did over here. We can resuspend and now get the slice tower for the 7th suspension of Hz. Okay, and so on the left, in both cases, we just get the 3-row suspension of whatever we had here. And 3-row suspension is just going to bump up the slice dimension by 3 times 2, which is 6. And so we know this thing is a 7 slice, and we know this thing is an 8 slice. And so that's the slice tower here. By the way, the row suspensions of Hg turn out to be pretty simple. So the row suspension of Hg aligns with the one-fold suspension. So again, that's something that is going to be showing up on the second problem set to think about that statement. But in any case, so here the fiber is concentrated in degree 4, it turns out. And so we found the slice tower. And so let's go and actually think about what that looks like. So here's the tower we just computed. So I've just rewritten it here. And whenever we have one of these, as we've talked about, we get an associated slice spectral sequence. And in this case, it's not super exciting. We have this H slice, which is in degree 4. And so there it is. You see it there. It's in, sort of column 4, and then that diagonal for the H slice. And then we have, on the other hand, we have our 7th slice, which is this spectrum. And to set up the E2 term of the slice spectral sequence, we have to compute the homotopy-Mackey functors of that equivariant spectrum. And again, this is the same sort of Berdon homology calculations. And so it turns out that the Berdon homology or the Mackey functors that we get for this 7th slice are a G and a Z in those dimensions. And then, well, there's only one possible differential that could cancel out these G's and leave us with the Z, the constant Mackey functor in degree 7 that we know we're supposed to get. So, there are multiple ways that spectral sequences are used. In this case, we already know what the answer is supposed to be. And so we try to fill in the pattern differentials that give us the known answer. Okay, so there's only one possible answer here. All right, so any questions about that first example? Okay. So let's think about another example. So instead of looking at an integer suspension, let's do a sigma suspension. And so remember, sigma is that sign representation of the group C2. And so we can look at the 2 sigma suspension, again, of HZ. And we know at the underlying level, it's just the ordinary, sigma 2 of HZ, which has something in degree 2. And so we might wonder, oh, is this a 2 slice, or does it have other slices? Okay. Now, again, for the group C2, well, we know that 2 slices are exactly row suspensions of 0 slices. And we know exactly that 0 slices are just Eilenberg-MacLane spectra. So we desuspend by row, and we produce something, and we ask, is this a 0 slice? In other words, does it only have a homotopy Mackey functor in degree 0, or does it have others? Again, we're left with a Verdon homology calculation to do. This is one we did before last time. And so we saw we get a Z sign in 1 degree and a G in another degree. So these are the Mackey functors that we computed last time for this spectrum. And again, there's a shift by 1. So here the Z sign shows up in degree 0, and this G shows up in degree -1. This is an Eilenberg-MacLane spectrum, so it's certainly a 0 slice. And then this one is now a -2 slice, again, because it's this geometric inflation or this pullback, which doubles the slice dimension. So in analogy with what we did in the previous example, this is now a -2 slice. Okay. So again, we found that this is the slice tower for this desuspended thing, but now let's resuspend by row, and that's compatible with a slice filtration. And so now we get the slice tower for the thing that we started with, which is this 2 sigma suspension. And so this HG, when we suspend it, again, this is part of this homework exercise I referenced, we just get an HG in degree 0. And then this one, when we suspend it, well, we get, of course, the row suspension of Z sigma. And it turns out that this is just the sigma 2 of HZ. Again, this is part of these Verdon homology calculations of the suspensions of HZ. I mean, another way to think about this statement is that the minus row suspension of HZ, let me write it here, the minus row suspension of HZ is the same as the -2 suspension of Z sigma. Okay, so again, if we're thinking about all of these in that homework that I suggested, then this is one of the answers that you'll find, and that provides this equivalence. Okay, fine. So we found the slice tower or slice filtration for this equivariant spectrum. It turns out we have a 0 slice and a 2 slice, and both of those happen to be Eilenberg-MacLane. As we saw in the previous example, it's not always the case that a slice is itself Eilenberg-MacLane. Right here, we had the 7 slice, which had more than one homotopy Mackey functor. But in this case, both the 0 slice and the 2 slice are Eilenberg-MacLane. So they just sit at the 0 line of our spectral sequence. And this is a very boring spectral sequence, even more boring than the previous one. There's nothing going on. It just collapses at E2. And so this is one example where the slice filtration for our spectrum happens to line up or be exactly the same as the Postkov filtration. They're both non-trivial, but they happen to be the same filtration in this case. Okay, so any questions about that example? So as you can see in both cases, we're really leveraging a number of things. Number one, that suspending by the regular representation just shifts the filtration and brings things into a range where it's more easy to understand. And we have an understanding of 0 slices and 1 slices just coming from homology calculations. So that's a really useful technique. All right, so let's go to C4 now. And let's think about the lambda suspension of HZ for C4. Remember, lambda was this 2-dimensional rotation representation. And so in particular, it's not the regular representation. And so it's not a priori clear how this interacts with the slice filtration. We know the slice filtration interacts very well with the regular representation row, but with some other representation, there can be some interesting behavior. So here, again, I've chosen something that's not the regular representation, and let's try to think about what slices might this have? What's the slice tower going to look like? And so again, because lambda is two-dimensional, when we restrict it down to the underlying spectrum, we know we have something in degree 2, right? We're going to have a z in that pi 2. And so that tells us automatically we have a two-slice, right? And we can think of that, that's detected by restricting from C4 all the way to the trivial subgroup. Okay. But what else might we have? Well, another thing we can do is, why did we restrict from C4 all the way down to the trivial subgroup? We could have restricted from C4 down to the C2 subgroup, and we might learn more information that way. And so what happens when we do that? So let's restrict down to C2. And so, there's a couple things we need to think about. So we have this lambda suspension, and then we have the Eilenberg-MacLane spectrum. And essentially, we can just think about those things independently. So one thing first is, what happens when we restrict that lambda representation down to the C2 subgroup? And so remember that lambda was this two-dimensional rotation representation, and the generator gamma in C4 acted by rotation by 90 degrees. And if we think about gamma squared, which generates the C2, that's rotation by 180 degrees. And so if we think about that, well, the x-axis is invariant under the 180, as is the y-axis. And what that tells us is that the restriction of lambda to C2 actually becomes two copies of the sign representation, right? So what we're saying is that the restriction of lambda is 2 sigma. And then moreover, so we need to restrict this C4 spectrum down to C2. And so it just corresponds to restricting that Mackey functor. And again, what this looks like is, for Z for C4, oops, is this picture where we have the restriction maps are the identity and the transfer maps are multiplication by 2. And when we restrict to the subgroup, we're just looking at only that part, which doesn't know about the C4 fixed points. So again, when we restrict, well, it's that constant Mackey functor for C2. And so that's why that's what I've written there. Okay, so now we're left with this spectrum. Hey, that's familiar. We just thought about that and we saw there's a 0 and a 2 slice, okay? So therefore, it follows that the C4 spectrum we're thinking about has to have at least a 0 and a 2 slice because we detect those by restricting to the subgroup C2. Okay, and theoretically it might have more, but at least we see those. All right. So let's see. So 0 slices, we're pretty happy about that because that's just a homology calculation or homotopy calculation. Now let's go ahead and find that 0 slice. Remember the 0 slice, what do? You just take the pi naught Mackey functor and then you turn it into a spectrum by making it Eilenberg-MacLane. And so we're left with thinking about what is pi naught of the lambda suspension of Hz. And well, this is one of the examples that we computed last time. We saw what the homotopy Mackey functors of sigma lambda Hz were, and it turned out that the pi naught was this B20 Mackey functor. B20 looked like this. It had a Z mod 4 at the top, a Z mod 2, and a 0 at the underlying level. So that's this Mackey functor that we computed last time. And so that will be the 0 slice then is this Eilenberg-MacLane spectrum. Okay. If we peel off that 0 slice, in other words, we take that map and take the fiber, well, then that fiber will be the slice cover, the P lower one. But in fact, I mean, this sequence is something that we looked at, again, last time. This is the Postnikov filtration. Again, it turns out that this thing only has a pi 0 and a pi 2. And so the fiber of this map is just sort of the Eilenberg-MacLane spectrum in degree 2. Anyway, and what we found was that the pi 2 was constant, Z, okay? All right, so now we're left to think about this thing and what slices does that have, right? Theoretically, it could have higher slices, but the claim is that no, in fact, this is a 2 slice. And so once again, this example, the Postnikov filtration will agree with the slice filtration. Okay. But this is not immediately obvious, so that's what we're left to think about. Any questions on this page here? All right, so again, this is sort of what we're looking at right now. We have the zero slice, we have this slice cover, which retains all the higher slice information, but we claim that actually, no, there's only a two slice. But again, to understand whether something is a two slice for the group C4, it's not quite as simple as it was for the group C2. So how can we think about that? Well, being a two slice means, on the one hand, that it's that it's greater than or equal to 2, right? It's slice 2 connective, and it's also less than or equal to 2. It's slice 2 co-connective, and we can just sort of show both of those properties independently. And so for the connectivity, the fact that it's slice 2 connective, well, I mean, this is an Eilenberg-MacLane spectrum in degree 2. It has no lower Mankey functor, so it's 2 connective in the Posnikov sense. And it turns out that that's stronger than being slice connective, and so there goes that implication. We'll actually talk about a slight generalization of this in a bit, but in any case here, if you're n connective, at least if n is positive, then that implies slice connectivity. So then we're left to think about, well, why is it less than or equal to 2? Why is it slice 2 co-connective? And so here, let's remember, what does it mean to be less than or equal to 2, right? So x is less than or equal to 2, that means that when we map slice certain generators for our slice categories in, so h up to g of multiples of the regular representation for the subgroup into x, that should vanish as long as the dimension, so k times the dimension of h is bigger than 2. That was sort of the definition that we gave. And so one thing I want to focus on is that, okay, if we look at the case where H is a proper subgroup, then again, I should have written the upper G here. By adjunction, this is really sort of an H equivariant statement. It's really a statement that the restriction down to H is appropriately co-connective, okay? So again, here, if we have the C4 spectrum, we can think about the restriction down to C2. And well, the restriction of this Eilenberg-MacLane spectrum is the corresponding C2 equivariant Eilenberg-MacLane spectrum. And again, on the homework, I've asked you to show that that's one of the examples where it turns out to be an n slice. So let's take that one for granted, that we know that restriction is a two slice. And so then we're just left to think about this situation where it's not induced, but rather we're looking at multiples of the C4 regular representation mapping it, okay? And again, we have this condition on the dimension, but that's what we're left to think about. And these kind of sort of inductive arguments where you assume you know what happens on the subgroups and then are left to think about what happens on the total group, that's very typical. Okay, so like I was saying, now we're just left to think about the C4 regular representation, and we want to show that these vanish, so we don't have maps from regular representation spheres, at least as 4k is bigger than 2, which happens if k is positive. And so let's just think about the case where k is equal to 1. So again, the claim is that we don't have any maps from the regular representation sphere into this sigma 2 hz. Well, another way to write this, again, both of these are invertible, and so we can move things to the other side. Let's move the 2 to the left, and let's desuspend by rho and put it on the right. And so this computation is the same as asking about the homotypic group pi minus 2 of this rho desuspended Eilenberg-MacLane spectrum. Okay? So once again, we're left with one of these Redon homology calculations to do. So this one is not one that we did together, but I claim that if you do this calculation, you get 0. And like I was saying last time, if you want to just look this up, this is in the HHR C4 paper. It's at figure 3 in that paper where they do all these suspensions. And so you can just see there's no pi2 there. In fact, there's no pi2 or higher. And when we increase k, we put more and more spheres in. I mean, these things are going to get more and more co-connective. And so it's also going to be true that the pi minus 2 of all of those will vanish, which is exactly the condition that we need. Okay. So again, what I wanted to highlight for you all is that showing that something is less than or equal to n, this is sort of a homotopy or homology calculation. Whereas so far the being slice connective doesn't have that field. Okay, so anyways, so by combining these two, we have verified the claim that this thing is a two slice. And so then this tower that we wrote down before, which was the Postnikov tower, we've now seen, oh, actually that is the slice tower here. Okay, again, it's a case where the spectral sequence collapses, there's nothing really going on here. All right. So I was saying that, showing that something is slice co-connective is a calculation, whereas slice connectivity, at least by the definition, doesn't appear to be. But I want to advertise a result of Hill and Yarnall. I think this is also in work of Ullman, which does give you a sort of calculational way to think about slice connectivity. And so what it says is that a G spectrum is slice n connective, if and only if, when you look at the geometric fixed points with respect to all subgroups, then there's a formula for what the connectivity of those geometric fixed point spectra should be. And I feel like I should give a warning here. When you hear people talk about connectivity, there's two related but different words that you might hear. You might hear n-connected and n-connective, and you might expect those to be the same, but they're not. They're slightly different. So when we say something is connective for a certain number, that means that the homotopy groups below that number vanish. Okay, so in particular here, I'm using the orange h to denote the order of the subgroup h, and this fraction need not be an integer, but when we say, oh, it's connective for this fraction, we mean that all integers below this, the homotopy vanishes. Okay. So, all right, and so there we go. There's a statement about the ordinary connectivity of these ordinary spectra. Okay. So in particular, let's look at a couple examples of this. For the group C2, what does this tell us about being one connective? Okay. Well, when we consider the trivial subgroup, that's talking about the restriction, and it says the restriction is one connective. All right, 1 divided by 1, still 1. And then the geometric fixed points are now 1 over 2 connective, but 1/2 connective is the same as a 1 connective, right? Because we're saying all integers below 1/2, the homotopy should vanish. That's the same as saying all integers below 1, the homotopy should vanish. And so here we're sort of recovering the statement that I made on the first lecture that actually being slice 1 connective is the same as being 1 connective in the Postnikov sense. Okay? So degree 0 and degree 1 are the two cases where those line up. But as we'll see in a second, degree 2 is not quite the same. All right, so let's use this Hill-Yarnall result now to think about being slice 2 connective. Okay, and again, at the underlying level, it's that same number. So the underlying spectrum should be 2 connective, right? So it shouldn't have a pi1 or anything lower. But now for the fixed points, the connectivity drops. So it's a weaker condition on the fixed point. So the fixed points are allowed to have a pi1, whereas the underlying spectrum cannot. Okay. In the case of C4, so we're going to do an example on the next page where we will show that something is -3, a slice connective. So also I want to highlight that this does work when it is negative. And so what does it mean to be -3 slice connective according to this formula? Well, the underlying spectrum should be -3 connective, so no homotopy below -3. The C2 fixed points should be -3/2 connective, so no homotopy in degree -2 or lower. And the C4 geometric fixed points should be -3/4 connective, and so that means no homotopy in degree -1 or lower. Okay, so again, these are sort of pretty concrete things, definitely calculational description. Now, I also want to mention that there is, if you look at the Hill-Yarnell paper, they also give a version of this with categorical fixed points rather than geometric fixed points. And so depending on the situation, the geometric or the categorical can be more easy to think about. Unfortunately, the categorical statement only works when n is non-negative. That one doesn't quite work out for n negative, whereas the geometric fixed points one does work even if n is negative. Okay, so let's look at a couple of examples. And so we'll start with the one suspension of HG. Again, we already know this. This is a two slice from the pullback story. But let's just sort of think about it from this condition over here, that being two connective is a statement about the underlying and the geometric fixed points. So first, the underlying. Well, remember that this is a geometric spectrum. At the underlying, the Mackey functor vanishes and the spectrum vanishes at the underlying level. And so if we have a trivial or contractible spectrum, well, that's n connective for any n that we'd like. In particular, it is two connective. But what about the geometric fixed points? Well, the first statement is that the sigma 1, we can just pass that out of the geometric fixed points. And so we're left to think about the geometric fixed points of this Eilenberg-MacLane spectrum. And so this is one case where the categorical fixed points of an Eilenberg-MacLane spectrum are dead easy to compute, right? You just sort of take a part of the Mackey functor and that's it. Geometric fixed points turns out to be a more interesting story. But in the case of HG, it turns out that there's nothing too interesting that happens. In this case, the geometric fixed points happen to line up with the categorical fixed points. Again, that's something I'll ask you to think about in the homework. And so we just get this, the Z mod 2 in degree 1. Okay. In particular, it is one connective. And so we do see that drop in connectivity here. But that does tell us it's slice 2 connective, as we already knew. Okay, and so let's do a C4 example here. And this is the minus lambda minus sigma suspension of HZ. This is the same thing as the, we could write this as sigma minus rho bar. It's the reduced regular representation where you've taken the regular representation and you've pulled out the fixed part. And so again, what we're going to see is that this turns out to be slice -3 connective. So as we saw over here, there are 3 different conditions to check about the fixed points. The first thing is the restriction to the underlying, and so that's just -3 HZ, which is -3 connective. And then we have the C2 and the C4 geometric fixed points to think about. And for C2, so again, geometric fixed points, one of the nice features of this that we saw is that it's a nice symmetric monoidal functor, strong monoidal. So in particular, this desuspension is really a smash product of 2 things, right? There's a representation sphere or a negative representation sphere and the Eilenberg-MacLane spectrum. And we're allowed to just think about the geometric fixed points of those 2 independently, okay? And so, here are the geometric fixed points of this with respect to C2. So, I just sort of have written that here, just whatever it is for now. But what's pretty easy to think about from the point of view of geometric fixed points is, representation spheres. And so there what we do is just sort of take the representation and just think about the fixed points of the representation itself. And let's see, so there's 2 parts here. The sigma is that sign representation. And again, there's a point of confusion here that this is a C2, it's a C2 representation. But remember, when we think of this as a C4 representation, we're really sort of pulling back or inflating along that quotient map. Oops. And so we're taking the sign representation for this C2, inflating it up to here. And then if we restrict it back down to the subgroup, it's going to be trivial. Okay. And so when we take the fixed points, this is fixed by the C2, and so that'll give us that 1 here. Whereas the lambda, as we talked about when we restrict that, lambda restricts to the 2 sigma. It's that rotation or 2 copies of the sign. There's nothing fixed there. So the lambda just goes away when we compute fixed points here. Okay, so anyway, so here is what we get. We get this one-fold desuspended copy of the geometric fixed points. The geometric fixed points are not that hard to compute, but in any case, if we expect this to be a connective spectrum, right, 0 connective, then even without computing the geometric fixed points, if we believe that it's 0 connective, then we see that this thing is -1 connective, which is what we wanted. And similarly for the C4 fixed points, what we wanted was that this was, that we didn't have anything in negative degrees, really. So in other words, we want the C4 geometric fixed points to be 0 connective. And here, these representations don't have any C4 fixed points, so those entirely go away, and we're just left with the C4 fixed points of this. And again, I'll ask you to think about this on the homework, but again, if we just, it's I hope plausible that this is a 0 connective spectrum, and that's exactly what we needed. Okay, so these things do verify this statement that that this C4 equivariant spectrum is -3 slice connective. All right, any questions about these examples? Okay, so the other topic I want to mention today is ROG gratings. And this can happen at several levels. So first, what is ROG? Well, this is what's called the real representation ring of G. And there are several ways to think about it. But perhaps the most simplest way or the most relevant way is to take isomorphism classes of the irreducible representations of your group, the real ones, and we're just going to take a free abelian group on those irreducibles. Okay, so the point is that every representation decomposes as a sum of the irreducibles. And so this kind of describes everything. And in fact, I'm writing isomorphism classes of irreducibles. It's really better to actually make choices of representatives of each of these isomorphism classes and just take those specific choices and take the free abelian group on those. So in particular, here's a few examples, groups that we've been working with. So for C2, there's two irreducibles, the trivial and the sign representation. And so the representation ring is this rank 2 free abelian group. Yeah, and this is a ring, but actually the multiplication is not really relevant for what we're talking about. So we're just going to use the additive structure. For C3, we have the trivial and then that irreducible rotation representation that we talked about. For C4, we have, again, the sigma, the sign, the inflated sign, and the rotation. And here, we haven't really talked about the Klein 4 group, but the point is that we have 3 different projections or 3 different surjections from the Klein 4 down to C2. And you can inflate the sign representation along those 3 different projections. And that gives you 3 different inflated sign representations for the Klein 4 group. And those turn out to be the irreducibles. Okay. And so, like I said, it turns out that rather than just grading homotopy groups or Mackey functors, et cetera, over the integers, which is what we've been doing so far, sometimes it's useful to actually grade over this larger ring or really just abelian group. Again, we're not really using the ring structure. And so the idea is that, if we have 2 representations, V and W, an element here is kind of like, it's a formal difference of 2 representations. It's a formal linear combination of the irreducibles. There's several ways to think about it. But anyway, so if we have some formal difference of representations, then we can form that sphere. And really what that means is take the SV and then the inverse of SW. So remember, one of the features of the equivariant stable category is that the representation spheres do become invertible. So that's how we make sense of this. And so then we can talk about a homotopy group indexed by that formal difference, and we just map this, this formal representation sphere or virtual representation sphere into our X. And then we can actually promote that to a Mackey functor. So at some subgroup H, you just sort of restrict everything to the H level, and it turns out that those assemble into a Mackey functor. Okay, so just by sort of including the things that we map in, that sort of the test objects, if you like, then we now get an ROG graded Mackey functor for any G spectrum. And it's become commonplace to use sort of a fancy star or a 5-pointed star when we're talking about an ROG grading, whereas we typically just use like an asterisk when we're thinking about Z grading. I think this notation is due to Hu and Krige. Okay. And so, for example, if we have, if we want to look at the homotopy Mackey functor of the sigma D suspension, right? So this is again one of these virtual dimensions of this spectrum. Well, this turns out to be something that we've already thought about, because this is really mapping from the minus sigma sphere into our spectrum. But again, mapping from the minus sigma sphere into our spectrum, well, we can just smash everything with S sigma. And so that becomes the same as mapping S0 into the sigma suspension of our spectrum. And well, lo and behold, this is a calculation we've done. We saw this Mackey functor is this geometric Mackey functor. So again, a lot of these things are just kind of repackaging information in different ways. So a lot of this is, again, these Berdan homology calculations, but it can be useful to keep track of them in different forms. Okay. So what about multiplicative structures? This came up a little bit in the sort of towards the end of the first talk when we were looking at that slice spectral sequence for KR. We allude to some of the differentials we know for multiplicative regions. And so if we have a ring in G spectra, then we can sort of multiply homotopy classes. And just as we would expect from integer grading, the representation grading, even if it's virtual, it adds. Now, even better, if we have a commutative ring, then we get a graded commutative ROG graded Mackey functor. But I've put a warning sign here because, sorry, was there a question? Okay, I thought I heard something. I put a warning sign here because usually when we talk about graded commutative, we're grading over the integers, and here we're grading over some more complicated ring. And it turns out that the graded commutativity is more complicated here. And so I'll sort of say what this looks like for the group C2. But again, in general, this is a bit of a delicate issue. So for the group C2, let's say we have two homotopy classes for our ring spectrum R. One is an I plus K sigma. So remember, we have two irreducibles, the trivial and the sine. And so for C2, our homotopy, the ROG grading turns out to be a bigrading because there's two irreducibles. So if we take I plus K sigma and J plus L sigma, then we can multiply two homotopy elements, and then the result will be in degree I plus J and then plus K plus L sigma. And we might ask about the commutativity there of that multiplication. And so it turns out that the formula, alpha times beta, so again, alpha is living in this one and beta is living in that one, can be compared to the multiplication in the other order. And there's the sort of a sign that we expect. This is sort of the usual sign from the I and the J part. This is the usual graded commutativity. But that's not the whole story. There's also another sort of sign. It's a certain power of something called epsilon here. And so what is epsilon? Well, epsilon, I wrote equal here. Maybe I should say it corresponds to the braiding or the symmetry isomorphism for the sign representation sphere, right? So, G spectra is a symmetric nodal category. For any object X, we have the twist map from X smash X to itself. In particular, for S sigma, that's a map. It's not the identity. And so now you have to be a little bit careful, but so after using some canonical isomorphisms, this is then an endomorphism of S2 sigma, which you can then desuspend and get as an endomorphism of the sphere. And well, endomorphisms of the sphere, that's pi naught of the sphere, which turns out to be the Burnside ring, right? So this is an element of the Burnside ring, A of C2. And it turns out to be a unit in the Burnside ring. So this is kind of the typical situation where the graded commutativity involves multiplication by powers of units in the Burnside ring. For C2, these two generate the units. But in general, you kind of have to look at these bratings for the various irreducibles that you have. There's a nice article of Dan Duggar that explains this. This is also discussed in an appendix of an article of Lewis and Mendel. Anyway, in general, it's somewhat complicated. So however, we're going to look at a couple, well, really the example of KR again here, and just sort of think about the multiplicativity there. And it turns out that if you use the sort of the unit map for the ring spectrum KR, then we get, then our pi naught here, which is the Burnside ring, then maps to the pi naught in either of these, which is just the constant Mackey functor. And there, the epsilon for the sphere does go to -1. And so in these rings, at least, it's a little bit simpler. But in general, you do have these epsilons around. Okay, so like I said, I want to think about, or I want to display really the ROG graded homotopy or spectral sequence of KR. And so in order to do that, I'm just going to introduce a couple of elements that are going to show up in the ROG graded homotopy. One of them is that for any representation, we can always include the fixed points into the representation sphere. And that element is typically denoted A sub V. And up to reindexing, it's an element of pi minus V of the sphere. And so we'll be thinking about this in the case of C2 for the sign representation. And so that we'll drop the subscript sigma and just refer to this as A. So it's an element it's a map from S0 to S sigma. And sometimes we desuspend it and think of it as a map from S sigma to S0. One thing that's useful here is that we have these cofiber sequences that we've studied before. Here's the sort of the dual cofiber sequence. And again, one thing that I asked you to think about on the first problem set is sort of what happens when we map out of this sequence. Okay, and what you learn from this one is, well, depending if you map out of or map into, these two sequences give rise to important or useful statements on the ROG graded homotopy. In particular, if we have a Mackey functor, the image of a transfer map is going to correspond to the kernel of multiplication by alpha. And similarly, the kernel of a restriction map is going to correspond to the image of alpha. We'll see this in action in a minute, but that's a useful thing to know. The other element I want to introduce, if we have a representation, is an element called U. Again, I'm using this convention of the, if I have a representation, then writing in orig is just the underlying dimension. And so this element U here is going to be, it's a homology class or homotopy class, depending how you think of it. And there's the grading. So it's in homotopy, it's the underlying dimension minus the representation. So this is an ROG grading. And this doesn't always exist, but it exists if V is an orientable representation. And so one thing about this class is that it restricts to a unit in the underlying homology or homotopy. So for us, we're going to be thinking about the group C2. And in that case, it turns out the sign representation is not orientable, right? If you act them and you're going to reverse the orientation, but two copies of the sign representation is orientable. And so that means we do get this class U2 sigma in the 2 minus 2 sigma homotopy of HZ. So those are going to be some important elements for us. Okay, so here is a picture of the ROG graded homotopy of HZ for the group C2. This picture corresponds to this homology calculation that, again, I asked you to do. So, if you look at the 0 line there, that's just the Z because that's the only Z-graded Mackey functor of this. If you look at this line down here, this is this calculation that we did before. I mean, this gives you the the homotopy of the these are the Mackey functors of the form something minus sigma of HZ, and again, that's the same as computing the homotopy Mackey functors of the sigma suspension of HZ. So this is this calculation that we did. We found this Z sigma and the G, and those are what show up here. Okay. So again, this picture is really these homology calculations. So again, there's this geometric Mackey functor. This is the constant Mackey functor. This is the dual. I'm sorry if it's a little bit hard to see, but there's a dual there. There's a dual there, and then we also have the sigmas, these sine ones. I'm going to zoom in a second, so hopefully it'll be easier. And then we also have this quotient of the sine module. Okay, so these are these various Mackey functors we've encountered, and it turns out that that is a picture of the ROG graded homotopy. The way that I've chosen to display it, this sort of matches up with some sort of motivic notation. That's why I like to do it this way. So here the vertical dimension tells you how many copies of sigma you have. So how many copies of that twist or that sine representation, whereas the horizontal dimension tells you just the underlying dimension. Okay, so like I said, let's zoom in a little bit. And so hopefully here it's a little bit easier to see. And now in the zoomed in picture, I've actually drawn in all of the elements that I introduced. So this element A, this is coming from this sine representation, shows up here in this geometric Mackey functor. And along these G's here, which are here, we get these various powers of A showing up. This other class U that I mentioned is showing up here. So it's the fixed points of this constant Mackey functor Z. Here we have this sine, which doesn't have anything at the fixed points, but has an underlying Z. And well, if we just think about the underlying, this is just sort of the homotopy of Z, and I'm using X to denote a generator of that underlying homotopy. So all of these in this column are going to have a power of X at the underlying level, but what changes is the fixed point level, and that's sort of the equivariant information. So here we have 1 restricting to 1. Here we have no fixed points. Here we have U, that class U, it restricts to X squared. And so again, that was one of the defining properties of U, is that it restricts to a generator. And so on. And so we have a sort of multiplication by that class A in this diagonal direction. So here's U, and here's A times U, et cetera. If you look up here, so here we have this quotient. Remember that quotient Mackey functor has the surjective transfer. And so we had the X minus 3 at the underlying level. And then the transfer of that X to the minus 3 is some class that we're calling theta. And theta turns out to be A divisible. And so there's theta over A and theta over A squared, and so on. And so here, we had this statement about how multiplication by A connects to restrictions and transfers. And we can see that there must be an A multiplication here because theta restricts to 0, right? Theta is in the kernel of the restriction. And so it must be in the image of A multiplication. So we know this class must be A divisible. And so that's how we can label that element, theta over A. We know it has to multiply to theta. Let's see. If we look down here, we have this constant Mackey functor here. The transfer of 1 is 2, remember in this? And so the image of the transfer is the kernel of multiplication by A. And so if we go 2 and then multiply by A, we learn that 2A has to be 0. And that's true because this Mackey functor is 2 tolerant. Okay. All right, so here's our picture of the ROG graded homotopy of HZ. And so let's just reconnect this with the slice spectral sequence for our connective KR spectrum. So before, this is the setup we talked about for the spectral sequence, but it turns out you can promote everything or improve everything to an ROG grading, as long as you're a little bit careful about how you set things up. And so again, this is what it looked like before. And now if we just put a representation in, it looks like this instead. So again, the orange V is the integer, is the dimension. So anyways, this is just the grading convention. So again, the differential just decreases the homotopy dimension by 1, even in the ROG graded sense. It just sort of subtracts off a trivial representation. And yeah, anyway, so this is what that looks like in the ROG graded sense. And again, if we have a commutative ring, then we do get a multiplication. It just adds, the ROG grading and just sort of adds a slice dimension as well. Okay, so let's look then back at this picture for KR. This is this E3 page that we wrote at the end of the first lecture. And so these are these D3 differentials we saw. And so, the last thing I want to do today is just sort of talk about what this looks like in the ROG grading. Okay. So again, I've just zoomed in on part of it now. So these are these Mackey functors where now I've labeled everything with elements. Okay. So here we have our Z with our class 1. This is constant. Up here, so I've written A times R1. So what is R1? Well, remember that the 2 slice here was this row suspension of HC2. If I think about this as a ROG graded object, the homotopy, well, that's a free module over the ROG graded homotopy of HZ with a generator, which I'm going to call R1, and this generator lives in pi rho of the row suspension. Okay. And so it turns out that, again, the element A times R1 lives in this degree, and here we have X times R1. Here we have A squared, R1 squared, et cetera. And here's the element at that fixed point level, in case you can't see it, is U times R1 squared. Okay, and so now this formula this differential that we wrote down before, in this, using these names of these elements, it becomes the D3 on U times R1 squared is A cubed R1 cubed. Now, actually, this element R1, it does live to homotopy. It's a permanent cycle. And so this sort of suggests that this formula should be true before multiplying by R1. And that's true. But this element U, we don't see it in this integer part of the grading. We have to move to a different part of the grading. Particularly, we have to desuspend it twice by sigma. In this picture, U is living at that -2 level, the -2 sigma level, rather. So if we look at the part of the grading where we desuspend by 2 sigma, all of a sudden there we see the element U. And so it turns out that there's a differential here hitting A cubed times R1, which is the class that lives there. Okay. Yeah, so sorry to be going a little bit long today. So this is again an understanding of the ROG grading of that spectral sequence we looked at before. And so the last thing I'll do is just display the corresponding ROG graded Mackey functors for KR, for the connective KR. So here's a picture in terms of the names of the Mackey functors, which, again, maybe a little bit hard to read. I prefer to, or often in these articles, you see people use symbols for the Mackey functors rather than names. And so here's the same information, but now using symbols. And so a square is Z, a square with an asterisk inside is Z dual. The orange square is Z sigma. The orange square with the purple bullet on top is the Q Z sigma. And then just the bullet by itself is G. Okay. And so here's a picture of the ROG graded homotopy Mackey functors of KR. And so, anyways, and again, I've drawn in the multiplications by A as these lines of slope -1 here. And there's one thing I just want to advertise in closing here. And so here, it turns out that we have these infinite A towers, multiplication by A. It gets killed off in most of the spectral sequence, but here on U, and then here, this is U squared is the element there, and all powers of U squared, turns out that the A multiplications on U squared do not get truncated. In the connective version of KR, they do get truncated, but in the connective version, they do not get truncated. So we see all these A towers, and these A towers, again, this is this first problem on the homework. The problem set is saying that looking at inverting A calculates the geometric fixed points. And so from this picture, one of the benefits we get is we see the geometric fixed points in this ROG graded homotopy. Okay, so what we do for the geometric fixed points is we look to invert A, we look what's not A torsion, and A goes down to the left by 1. So everything up here certainly gets wiped out, but we get an infinite A tower there, another one here. And so again, it's these powers of U squared that survive. Okay, so sorry to go a little bit longer today. That's what I wanted to discuss. And so next time, hopefully we will get a chance to talk about some of the duality that I was hoping to talk about today. There's also an important notion of norms that shows up. And I hope to talk about the spectra MUR or BPR. Okay, so that's where we'll stop for today.